These are pre-calc notes for Blitzer 11.1 using finding limits using tables and graphs. So first, we're just talking a little bit about notation. I know we've used this a tiny bit in Algebra 2 and then at the beginning of the year in pre-calc. But what this, how we would say this right here is the limit of f of x as x approaches a. So you can see how limit, because of the word limit, of f of x of my function as x is approaching a, so x is getting closer and closer to a, is L. So that's how we would say that out loud. The limit of f of x as x approaches a is L. So my limit would be equal to L. And remember, a limit is like when I get really, really close to something. What is going on? It's one of our big ideas, I would say, behind calculus. We're always looking at what's happening at a point, and then area is the other thing that we're looking at, area under a curve. So for example 1, we just want to find a limit using a table. And the first few problems on your homework are going to be like this, where the table is provided. And I can see I still did not fix that number right here. So you can see in the top, our x is getting closer and closer to 4. And that's what we're looking at here is our limit as x approaches 4. Same thing when I am going the other direction, when I'm coming from the right, my x is getting closer and closer to 4. And then the limit is this idea of like, well, what's happening exactly at 4? What number are we zeroing in on? And we can see that here it's getting closer and closer to 48. 48 is just a little bit bigger. And then in this other direction coming from the right, 48 is just a tiny bit smaller. So 48 would be that number that would fit in the pattern. So a table would be one way to figure this out, but it's also an awful lot of work to take all these values and plug them in for x and then go through and work it out and make a table. So a table is normally going to be our absolute last resort. We want to find a limit any other way, but not a table. But I do think the table gives you a good idea of what a limit really is. So honestly, for a problem like this, what I would do is I would just simply substitute the 4. So let's see what happens when we do that. So for finding the limit as x approaches 4 of 3x squared, there's nothing here to prevent me plugging in 4. There's no denominator that's going to become 0. There's nothing weird like that. I could just do 3 times 4 squared and directly substitute, which is 3 times 16, which is 48. So we could get 48 that way as well. So this 48 is the limit as x is approaching 4. It's also the value of f of 4. So let's think about that. So sometimes we can just directly substitute. We're going to look at a couple examples where we're trying to find a limit. This is one that we're going to skip this year. We're going to skip this year anything with logs or sines or cosines. So anything trig, anything log related. It's just going to make it easier this year. So this is the problem we actually want to look at. So on this one, I notice when I try to directly substitute that -3 plus 3 is going to make a denominator of 0. So one of the strategies you're going to have to use on your homework, because we don't want you making a table. So if you were going to make a table, you could just make a table for this, but we really want to avoid that from the get-go, is I could try factoring. So on the first one, we directly substituted. Here, I'm going to try factoring. So the limit as x approaches -3 of, let's go ahead and factor, x plus 3 times x minus 3 all over x plus 3. So because I can get rid of those factors of x plus 3 and simplify this, now I have just an x minus 3. And now I can directly substitute. -3 minus 3 is going to be -6. So sometimes I can find the limit by just kind of playing around. So this problem over here is one where we really have to graph or make a table. And that's why, another reason why we're skipping it. So we're really trying to simplify what we're doing this year. The next few examples are going to center around graphing and how limits look on a graph. So the first one says limit as x approaches 4 of f of x. So this whole function here, this line that I have, this curve, is labeled as y equals f of x. So when we're talking a limit, we're talking about like if I am looking at this function and x is approaching 4, because that's what I want to find is as x approaches 4, what number kind of fits in with that pattern would be on that line. So I want to think coming from the right here coming from the left. So, and I'm zeroing in on this open circle right here because this is where my x is equal to 4, right? This is 4 on my x-axis. So as I get closer and closer to x equaling 4, what number would make sense, would just kind of fill in that hole and be on that graph. So I am finding, when I'm looking for my limit, I'm really finding my y value. So let's see, it looks like y here would be 7. So my limit as x approaches 4 of f of x would be 7. Just based on, if I think about how, like, as I'm getting closer and closer to x is 4, this is increasing, right? It's going to be like 6.9, 6.99. So 7 would be that next number that makes sense. So the limit does not necessarily have to equal the value. So this is the limit. And then when I'm looking at f of 4, I'm really looking at a value. So my issue here is that when I'm actually finding f of 4, I have this point over here that's solid and filled in that shows me when x is 4, my y is 2. So the value when x is 4 is actually 2. And that's because I have this open circle right here. So sometimes the limit doesn't necessarily equal the value. So I can find the limit as x approaches 4, and that's one number, but then my actual value is going to be different. So you're going to see a lot of kind of funky graphs today. So on the next one, we are looking at actually doing our own graph, and it is a piecewise function. So on a piecewise function, I know that what I'm really doing, and I don't know why this notation still seems to be bothering people, but I look at this and I really think, well, y equals 2x minus 4. It says if x doesn't equal 3. So everywhere except 3. Everywhere except when x equals 3, because it's only when x doesn't equal 3 that I have that. So if x does equal 3, I have a negative 5. So because this is only when x equals 3, I have a y value of negative 5. That's really going to be an ordered pair, 3, negative 5. All right, so let's see if we can put all this together. So y equals 2x minus 4. I've got a y-intercept and a slope. So I'm going to go ahead and graph this. And this is probably enough points. Except now it says x can't be 3. So then what I'm going to do is I'm going to go over to my graph where x does equal 3, and then go up to that graph. And when x equals 3, I can't actually have anything right here. So this is going to be an open circle. And I tried to make it really obnoxiously big. And I might try to even erase what's inside, but I don't think I can erase this. So I have an open circle right here where x is 3. And then maybe I will try to fix it. It's really bugging me. There we go. It's a little bit better. But then I know I also have this point, 3, negative 5. So this is a lot like the last graph I did. And now we're looking for the limit as x approaches 3 of f of x. Well, again, my limit is like on my graph as I get closer and closer to x equals 3. So I know that as x is getting closer and closer to 3, here's 3 right here on my x-axis, that my y is getting closer and closer to 2. That's that number that would make sense on my graph. If I take it an extra step, though, I would find once again that when I find the value of my function at 3, so when I find f of 3, it doesn't actually equal 2. It actually equals this dot down here, my negative 5, that point. So there's basically 3 different kinds of graph situations that we can have that we want to kind of keep in the back of our minds as we're working through this today. The first one, you can see I am trying to find, here's a right here. So we're talking about our limit of our function as x approaches a. So as x approaches a, my y value is L. And if I had to find f of a, that would also equal L, right? Because this is a solid filled in circle. So what we have here is we have that the limit is the same as the value. On my next graph, if I think about my limit of f of x as x approaches a, let's see what that's going to equal again. Well, here's a. As x is approaching a, it doesn't matter that this is an open circle right here. and my graph actually doesn't equal L, my limit can still be equal to L, because the limit, remember, is just what we get closer and closer to and what would kind of make sense. So my limit's going to equal L. But if I go to find f of a, it's not defined. I don't have f of a anywhere. So on this one, I have a limit, but no value. On my last one, when I find my limit as x approaches a of f of x, once again, it's going to equal a. So when I follow my graph up to a, my y value is L. But when I find my value of f of a is something different, right? It's way up here. So it's not going to really be equal to L. I have no idea what it is, but it's not L. So on this one, we have a limit and we have a value, but they're not equal. So 3 different kinds of graph situations that we can have. So you're going to find that there's some maybe a little bit more complex piecewise functions. For the directions for the homework today, if it says make a table, you're not going to make a table. You're going to just try to directly substitute. On the problems where it says graph, we really do want you to graph. You're going to need some kind of graph paper, and you're going to be getting your information off the graph. So if it says graph, please graph it. If it doesn't, you can use the other methods that we looked at today in class. So this is the end of our 11-1 notes.